Hi all, a very good morning to all of you. A very warm welcome to everyone who have taken out time to engage in community event, to learn something and to share knowledge. It's a great pleasure for us to bring a yet another exciting tech talk for our community members. Our endeavor has always been to bring the industry experts to this stage and share their knowledge and expertise. Our today's speaker is Akhil Soni. He has pursued dual degree BTech plus MTech from Computer Science Department from IIT Delhi. He started in 2013 and ended his course in 2018. Post which he joined as a software developer in IBM. In his current role, he is working as an analytics engineer at Schlumberger, and his work mainly lies in the areas of machine learning. His skill sets include computer vision, NLP, and Python. Uh, and he is also a deep learning AI ambassador and speaker. As a part of community, he speaks at various open source and community meetups and events. So that was a brief introduction about Akhil. I would now like to hand over the stage to Akhil to start off with the presentation.
Okay. Thank you, Nirav, for the introduction. So I hope you all can see my screen and I am audible enough. So, okay. Good morning, everyone. So this session is about a deep dive into machine learning and how we can explore various concepts in machine learning and bring them to life. Okay. So let's start our presentation. So what is machine learning? So this is a famous image available on the web. I got it from Edureka. So what exactly is machine learning according to you? So as the name suggests, machine learning. So it's a way wherein machine learns on itself. So before I go into the technical definitions and all, I would just like to proceed and explain what is machine learning with an example. So so suppose you have a set of inputs and outputs over here. So for example, when the input is 0, you get the output as 32. When the input is 8, you get the output as 46.4, 15, 59, 22, 71.6. So this is a given data which you have. Okay. And now if you are asked that what will be the output when the given input is 38. So how will you do that? I mean, obviously all of us would try to figure out some pattern between this input number and this output number and this series, and then whatever pattern which we may conclude upon, we would then predict the value of this number. So like for example, if I try to if I try to just think about it, what it might be. So it might be like 8, so basically it's 5 times plus 6 or something like that. But yeah, basically we would try to figure out these patterns in these points. What else can we do? Maybe we can plot these numbers on a graph and then try to see and then try to predict what would be the value for 38. So this is exactly what a machine would do. When we say machine learning, we would just give this input and output data to our machine and then expect that the machine itself comes out with an solution or with a relation between the input and the output, and then given any new input value, it predicts the output value. So what do I mean here? So let's go ahead and first answer this question. So basically the answer to the 38 will be 100.4, and this is basically a Celsius to Fahrenheit conversion. The input values are the values in degrees Celsius and the output values are the values in Fahrenheit. So we all know the conversion from Fahrenheit Celsius to Fahrenheit is Fahrenheit equal to Celsius into 1.8 plus 32. So basically you multiply the input number with 1.8, add 32. So you do so on and you get the answer as 100.4. Okay. So how will we approach to solve this problem as a part of machine learning? Let's see. So before that, how is it different from a traditional software development? So basically in traditional software development, we know the input and the algorithm, and then we write a function to produce the output. Basically we just have input data, we apply logic to it, we produce output. But in machine learning, both the inputs and outputs are known, but the underlying algorithm is unknown that creates the output. So if I have to explain it, let's see here. When we say traditional software development, we know this algorithm, we know this logic, we know the equation that Fahrenheit equal to Celsius into 1.8 plus 32. We define a function, we say def cells to Fahrenheit equal to Celsius into 1.8 plus 32, return Fahrenheit. And then we just implement this function, we give the input as Celsius and we give the algorithm, and the function outputs your Fahrenheit value. So this is the traditional software development where we know the algorithm and the input, and we don't know the output which is given by our algorithm. But how is it different from machine learning? In machine learning, we don't know the algorithm, we know the input as well as the output, but the underlying algorithm is not known. So we expect our machine to come up with this algorithm based on the input and the output data. So if your input is 0, 8, 15, like if your input is a tuple, say for example 0 comma 32, 8 comma 46.4, 15 comma 59, and so on, we would expect our algorithm, machine learning algorithm, to come up with an relation between the two pairs, two values in our tuple, like how is 0 related to 32, how is 8 related to 46.4, and so on. So this is the difference between the traditional software development and machine learning. In traditional software development, we have 100% accuracy. As in, if I have to say, if you implement this function, this Fahrenheit value will be accurate to the 100th decimal. As in, it will be 100% accurate. Whatever Celsius value you give, it will be exactly equal to this Fahrenheit value. But when we come to machine learning approach, this accuracy might not be 100%. This might be 99%, 99.9%. So when I say 99%, what do I mean? So for example, if I have to say in my previous slide, if I have to ask what is the output for 38, our traditional software development will predict exactly 100.4. It will not give me 100.39, it will not give me 100.41, it will give me exactly 100.4. But my machine learning algorithm might give me something like 100.38 or 100.39, or maybe if it's less accurate, it might give me 100.1 or maybe 99.8, depending upon what is the accuracy of our machine learning algorithm and how good we have trained it. So that's the difference. So here we will rarely have 100% accuracy, because we are not giving it the algorithm specifically, we are asking our machine to come up on its own, which is a big thing, because we humans can make it out from looking the data that okay, maybe it's like 2271.6, it's maybe we can come out with this algorithm on our own. But for a machine to do so just on the basis of input and output, it's not that a small thing. Okay, so that's why when we say machine learning, we will rarely have 100% accuracy. So yes. Uh, so so my point being, when we give any input, the output might not be 100% accurate. So now let us see how will we solve this problem, this specific problem, with respect to machine learning. Before that, I'll take a classic example of housing price prediction, which is like the introductory problem to every machine learning enthusiast. Every machine learning enthusiast starts his career or starts his journey from this problem. So it's a very simple problem, wherein we have a set of 100 parameters or maybe 200 parameters, like size of house, which floor the house is, what is the floor rise, which area does the house belong, how many number of bedrooms are there in the house, or like what is the proximity of the house to the metro station, and so on. Basically there were some 150 to 200 parameters, and those parameters are somehow related to each other, and which gives us the value of the like house, what is the price of the house. But here, for the sake of simplicity, I have just assumed that we predict the price of our house based on just one parameter, which is size of house. So size of house can be in any dimension, like square feet, square meter. So let's go by the global domain, which is square feet. So from this graph, you can see that this graph is not labeled, but it's for just for your understanding purpose. So you can see that maybe a size of house which is here, like we can suppose this is 100, then this might be 40. So 40 square feet will give you this price, like $1,000 or whatever. Okay, and you can see that there is a general trend that as the size of house increases, the price also increases. But so given this is your input data, this is your points, but now our problem is that given a new size of house, what will be its price? So we have to predict what is the price of the house given a new data. So how do we do it? So forget about machine learning. If for ourselves, we wanted to decide how do we solve this problem. What we would have done, we would have just tried to make a straight line here, or try to fit a curve or straight line, so that we can estimate the future values. So this straight line is pretty much okay, it's a pretty much good approximation of the data. So for example, according to this straight line, this is our function. So when the input value is say 40, the output value given by our straight line is maybe $800, but the actual price is $1,000, which is not that far away from 800. And similarly, when we go up to this part, so this might be 80-70 square feet, and the price predicted by our model or our function is 1200 square feet or $1,200, and the actual value is might be $1,250. So basically, we would manually make, like, we would probably try different slopes of this straight line. Like we can try a slightly slanter line, and the purpose will be to minimize the error. That, and what is the error? The error is basically the difference between the actual value and the predicted value. Again, there are multiple types of error. This, just what I just mentioned, is your linear error, wherein we directly subtract the values. But there are concepts like mean squared error, which is more often used while calculating the error. So what is mean squared error? It is nothing but the square root of the summation of the squares of the two values. So basically, if this is your actual value and if this is your predicted value, so mean squared error will be square root of predicted value square minus actual value square, the mod of it, so that the square root doesn't get negative. So this is, so our ultimate aim is to minimize this error and come up with an ideal straight line which best fits our data. And then once we have the straight line, we can easily predict what is the price for a new house, for a new size of house, because basically this is y equal to mx plus c. We would have the values of m and c. So for example, this line might be y equal to 2x plus 3, and then if we have another x value here, which is the size of house, we can easily predict the y value. But again, will it be accurate? No, it might not be 100% accurate, because anyway, we are in our training data. This is known as the training data, which we use for our input. So this is how we predict the value. Okay, so this is how we will do it manually, as in if we didn't have any, if we just had this information and we would say, okay, let's plot it on a graph, draw a straight line, and then done. But what if the points couldn't be like, if the input data or of these points are not exactly feasible to if it's not exactly feasible to draw a straight line through it, what will we do then? So for example, the points are this way. Okay, so now here you can see that no straight line would fit this perfectly. So what would be a better solution would be a curve which goes like this. Okay, you can see this curve. So this is a more practical solution. But we can come up with this curve by using some techniques, like we can approximate this curve using saying ax square plus it looks like a cubic curve to me, so maybe we can say ax cube plus bx square plus cx plus d, and then we have this various points, and we can come up with the values of a, b, c, and d. Okay, so but you would assume that, okay, still the error is quite not that low, because here the error is 0 for this point. For this point there is some error. For this point there is a bigger error, and so on. But then you might wonder, what if I make a curve like this, which looks like a sinusoidal function, like this? The other black line you can see here, this, if you make a curve like this, then this probably is a better fit than the earlier curve, because here the loss is way lesser. But there is a problem here. In the machine learning domain, we call it as overfitting. So what has happened here is, your input data is the loss on your input data is very low, because you have drawn a curve which passes through each and every point, so that the so that your loss is like almost close to 0. But then what will happen when you get a new value of house, like new size in square feet? This model, which is a sinusoidal curve, will perform very poorly, because this function might go like a sinusoidal wave. Okay, and when you test it on new values, like the values which this curve has never seen before, values other than what is plotted here, this will give you very poor accuracies. And when I say accuracies, I mean very poor results, and the loss would be huge, like difference between the actual value and the predicted value. So this curve is not a good option. This, the earlier curve, which looks like a cubic curve, this curve is the better solution, because even though the loss on the training input, the loss on the given data is quite higher than the other curve, but the overall accuracy would be way better than the other one. So this is precisely what is known as linear regression. Whatever we just discussed, whatever I just told you about like fitting a curve, a linear curve, a polynomial curve, cubic curve, whatever. So this is known, this algorithm is known as linear regression, wherein we assume a curve beforehand. So for example, here in this slide, we would assume the curve as y equal to mx plus c, and then based on our input and output values, we would come up with the values of m and c. Here we would assume, looking on this data, we think that a straight line wouldn't do good, so we would assume that, okay, let's take a cubic curve, or maybe a polynomial curve, ax cube plus bx square plus cx plus d, and then based on this input output values, we come up with the values of a, b, c, and d. So this algorithm is known as linear regression. And so I would have explained what linear regression is in detail, but that is not in the scope of today's presentation. So if you have any doubts, you can still ask me post session. I would be happy to clear them. But this is in a gist, this is how linear regression works. Like, if for the input you just assume a curve, assume a polynomial curve, linear curve, any curve, and then you come up with the, at the end of the algorithm, you come up with the values of the variables like a, b, c, and d. Okay. And again, so here we just have one variable, which is size in square feet. So that's the reason we can assume the curve, like we only have one independent variable, x, ax square plus bx plus cx plus d. But what if here we had another variable called maybe floor, like floor rise? So then we would have to consider both the variables. So then our curve, the equation which we would assume, would somewhat look like a1 x cube plus b1 y cube, a2 x square plus b2 x square, a3 x plus b3 y, and plus c or d, whatever. So then we would have to come up with the values of 8 variables: a1, a2, b1, b2, c1, c2, and d. 9 variables. Sorry, 7 variables. So then again, these are, you can add, you can keep on adding more complexities in the problems. And in the real world scenarios, we deal with hundreds and 150, like literally on in terms of hundreds of parameters. So when we solve a real world machine learning domain problem, there wouldn't be just one independent parameter anytime. There would be like at least hundreds of independent parameters, and you would be expected to get a relation out of those 100 and 150 parameters. And linear regression does quite well in this domain. So yeah, but anyway, so I hope I could clear this, the concept of what linear regression is. Basically, it is very similar to what a human would do, given zero knowledge of coding and just given the input data. This is the first instinct, and that's why linear regression is the most basic algorithm in machine learning domain. So now let us just have a brief overview of what are the various applications of machine learning, just so that you know this is happening out there. So banking. Okay, so how is it applied in banking? One example will be like to estimate how often does a van need to visit ATM to refill the money. So it is not that it is not unorganized. There is It's not that, okay, every bank thinks, okay, we will just go randomly and we will just refill the ATM. No, it's not how it works. So they do a complete analysis. They see, okay, for example, if they put some 1 billion rupees or $1 billion today in the ATM, and then they have a track of the data, like, okay, it takes around 1 month or 30 days for it to for the cash refill to, or for the cash allocation to fall to zero. Then they say, okay, we'll go after 40 days. But then there are other parameters, like suppose it's a festive time, so people would there would be more people withdrawing money, and the ATM might get empty sooner. So again, there are such parameters, and then they come up with a model with all the parameters included, and then they come up with an ideal number of days. Like suppose, for example, one bank comes up with 20 days, so then they visit every 20 days and refill the ATM. It's not like they just go, because how will this affect? Because this is no, like this would affect the transportation cost. This would affect the this would have an impact on the on the manpower, because the ATM vans are highly guarded with high security because it contains a lot of cash. So yeah, these banks really make a ton of profit using just this simple logic or simple optimization. Then in the advertising industry, so you would all have noticed that you would see Google ads, or maybe we are surrounded by advertisements everywhere, be it an online game you play, or be it you scroll Facebook, scroll Instagram, whatever, there are ads everywhere. So again these ads are not like random. Okay, if you would notice, these days ads are becoming very central to what we think of. As in, sometimes it happens that I am thinking, or I discuss something about, I discussed about say chair, and immediately the next time I open Facebook, I see an advertisement of a chair in front of me. So how is all that happening? Through machine learning. The users, the big giants like Google, Facebook, Amazon, these people take our data, as in the data which is freely available, which we consent that okay, I allow my data to be used. So they take our data, they apply analysis on our data, and then they predict, and then they show us ads which we want to see. It's not like the olden days where we were seeing ads of completely random things which we are never interested in. And if you also realize, Google, if you Google ads, there is a feature of closing the ad, and when you click on close the ad, it asks you, why did you choose to close this ad, and it gives you four options, like this ad was not appropriate to me, too frequent, or say spam or whatever. So then they again use this to train their model even better. If you say inappropriate to me, then they tweak their model parameters, saying that this ad should not be displayed to this person because he thinks that it is an inappropriate ad and it doesn't concern his requirements. So again, the next time Google will show an ad, it will make sure that it's not the same ad, or it's not related to that domain. So this is happening right now. I mean, whatever which we are discussing now, everything. There are tons of data everywhere on the web which is freely available of all of us, and these are being used to lure us into purchasing things which we think of and which we want. So yeah, that's in the advertising domain. And healthcare. So healthcare is a primary domain wherein machine learning has done huge advancements. So for example, clinical imaging to assist doctors in reading MRIs, and genomics where DNA sequences are read. So all of these things are done by a program, and and to an extent that it has zero risks, because in healthcare we can't afford to have a 99.9% accuracy. We need 100%. So yeah, machine learning has reached that heights. And automotive. So this is a very ongoing domain which you all would know. Tesla, Elon Musk is like leading this front in the automation industry, in the with self-driving cars and whatnot. So this is already here. Self-driving cars are like, they have inbuilt intelligence in them, which tells them to stop on a green signal, stop on a red signal and proceed on a green. This is a very basic thing. But even like complex things, that if there is a roundabout and there is one car approaching from the other end which is not visible, how do I track it? Or so on. I mean the applications of machine learning are vast. In each and every domain around us, we are surrounded by machine learning in one or the other way. Okay. So yeah, now let's come to neural networks. Neural networks is another domain of algorithms which belongs to machine learning. One was linear regression, which was the most basic one. Neural networks is kind of a bit complex and more on the computationally intensive, and it involves a lot of mathematics. So basically, what is a neural network? Okay, so neural network, so the main aim behind the implementing this neural, or creating this neural network algorithm, was to simulate our human brain. Okay, so as you can see, this is a picture of a human brain, our human brain. Okay, and the primary unit of our human brain is a neuron, and these neurons are somehow related to the axons, synapses, dendrites, and these internally link up to create a signal. So for example, when you touch a hot object, these neurons are responsible for triggering your brain cells that okay, this is causing an inflammation on my skin, and that is bad for our body. So send a signal to your hand that you should not touch a hot object, and remove, and immediately your reflex action is to pull out your hand from the hot object. So all of these things are controlled by the neurons. And And this is how and this is the primary thought behind an artificial neural network. So this is a natural neural network which exists in our brains, and our brains have billions of neurons which are responsible for all of the things which we do: talk, speak, walk, everything, from ranging from most basic ones to most complex ones, wherein we wherein we actually write code for making artificial neural networks. So again, as similar similar to human neural network, and in an artificial neural network, the primary the primary unit is called as a neuron. So this is a typical neural artificial neural network diagram, wherein this all of these balls you see here are neurons, and this is the input data, or basically your, I'll come to it once. I'll just come to it. So what I'll do is, I would showcase you, I would help you understand the Celsius to Fahrenheit conversion with a neural network. So what we'll do is we'll implement a basic neural network, very basic neural network, and we would come up with a model on our own. Like, we would ask our machine learning model to machine learning to come up with a model on its own with the relation between Celsius and Fahrenheit using neural networks algorithm. So before that, I'll just give you an overview of how exactly it works. So the first layer is known as the input layer, the middle layers are known as hidden layers, and the final layer is known as the output layer. So this is the there can be one to infinite, or not infinite, but one to thousands of hidden layers in between, and one input layer, one output layer. So what does it mean? So input layer is basically the inputs of your data. So what, in our Celsius to Fahrenheit case, the input layer would be the Celsius values, and the output layer will be your Fahrenheit value. Okay. So when we say, when we here we see three neurons. So these three neurons each represent one parameter. So for example, in our Celsius to Fahrenheit case, we only have one parameter in input, which is the Celsius value. So our neural network won't have these two neurons. It will just have one input neuron and one output neuron, because we just have one parameter in input, which is your Celsius, and one parameter in output, which is your Fahrenheit. And the middle layers are responsible for like coming up with the function. So whatever model which we will come up with, these hidden layers are responsible uh, to come up with that value. Okay, so let me explain it to you on a level deeper. So consider the example of housing price prediction. Okay, so in housing price prediction, suppose we have three parameters. One is your size of house, floor rise, and maybe say number of bedrooms, or maybe say number of bathrooms, whatever. Okay, so we have three parameters. So in this case, each parameter will correspond to each neuron in this input layer will correspond to one parameter. Maybe this corresponds for your size of house, this corresponds for your floor rise, and this corresponds for your number of bathrooms. Okay, so then oh sorry so then, and your output is just one value, wherein your output is to predict the price of the house. But in output layer also we can have multiple values. I'll come to that later. But so the basically, these you can see, right, all the neurons in the input layer are connected to every neuron in the hidden layer, and so on. So this is known as a fully connected or a dense neural network, wherein this, you can see this neuron, if you see this neuron, it's connected to this neuron is connected to this. Basically all these three neurons are connected to all of the four neurons. So what happens is, there is a transformation matrix or a transformation function which converts these input layer into this hidden layer. Again, there is some different transformation function which converts this hidden layer into this hidden layer, and the final transformation function which gives you the output. So for example, when we say 0 degrees Celsius, there will be some computation here, and then we get the value as 32. So like without further ado, let me just implement this neural network, which will give you more clarity and as to how is it implemented. So again, I am not going into the mathematics of how a neural network is built and how are these functions calculated, how are these functions actually calculated, because these days we have libraries from TensorFlow, Keras, that automatically calculate these functions. So but if you are still interested, you can write a question, or you can write to me. I'll be happy to help. Okay, so now let's go to the uh, implementation aspect of neural networks. So one second. So I'll be using a Google Colab notebook. So if you all are aware, this is just similar to a Jupyter notebook, but it is on the cloud, on the web. So it is kind of easier and more user friendly than a Jupyter notebook. And we use all these notebooks to code because it's easier, and you don't have to rewrite the entire code again. You can just run the code and you can be done with it. So yeah, this is basic training like basic neural network for Celsius to Fahrenheit, which I have built. I will walk you through the each of the steps, and I will explain it to you how we can build a simple neural network. Okay. So first of all, we would be using a TensorFlow library. It's a Python library, and it is extensively used for machine learning in the machine learning domain. TensorFlow and PyTorch. These are the two leading libraries which we use. So each of them has its own pros and cons, but yeah, we'll be using TensorFlow as of now. So I say import TensorFlow as TF. So I click on this button to run it, just like for the sake of completeness, if you're not aware of what a collab is, Google Colab notebook. So let us wait, it's taking some time. uh, Sorry. Yeah, so it's done now. Okay, now I import some few other libraries, NumPy, logging. So NumPy is a library used to deal with arrays, matrices in Python, like multiplication of matrices, compute the SVD, eigenvalues. So this library makes it life easier for us in NumPy. And now, okay, so now we this is the part where we define our input data. So if you see the Celsius and we define two arrays, Celsius and Fahrenheit. Okay, and inside the Celsius array we define the values like -40, -10, 0, 8, 15, 32, 22, 38. And in the Fahrenheit we define the corresponding Fahrenheit values. Okay, and now, and I just print it, so the output would be something like this: -40 degrees Celsius is -40 degree Fahrenheit, -10 degrees Celsius is -14 degree Fahrenheit, and so on. So this is just the part of initializing the data, which we have. So again, in the machine learning approach, this is the only two things which are given to us: the input and the output. We are not given the relationship between these two, and we are expected to come up with a relationship here. So we will do that. Okay, so now these are some of the terminologies which I guess I discussed, but I'll just discuss again. So feature is basically the inputs to our model. In this case, a single value, the degrees in Celsius, which I just told you that in if we have a housing price prediction, we would have three features, or 3 or 100 features according to our requirement: a size of house, number of bathrooms, floor rise. Labels, oh sorry, sorry. For labels, the output our model predicts, in this case a single value, which is the degrees in Fahrenheit, which again I just mentioned. And then we can say the same thing, a tuple. I also said, right, we have a tuple, input and an output, 22, 72, and so on. So now we go on to build a neural network. Okay, so we create the model. We will use the simplest possible model we can, because it is a very simple problem. I mean, using a neural network to solve a problem as trivial as Celsius Fahrenheit um, is like using a axe to cut an apple. So because neural networks have huge power, and this is a very simple problem, but for the sake of better understanding, I am using this so that it's easier for all of you to grasp what is a neural network. Okay, so yes, so now we will create an input layer which will be of shape 1, because as I said, there is only one input feature, which is the value in Celsius. Okay, and then we have one neuron in it. Okay, so we create the input layer as L0 equal to TF is TensorFlow, Keras is a class or like a sub module of TensorFlow, and then we say Keras dot layers dot dense means again the same thing here, like all the neurons are connected to each and every neuron. That means if we say dense, then that is what it means. Okay, so tf dot keras dot layers dot dense, units is 1 because we have just one neuron, input shape is 1. So basically when we execute this command, it is equivalent to, in this diagram, it is equivalent to replace this input layer with one neuron. That's it. Okay, So let me run it. Okay. So now we want to assemble our layers into the model. So what we are saying is, once layers are defined, they need to be assembled. Basically, we need to connect each of the layers. Okay. So we are using a sequential model. Sequential model basically means like we'll first make the input layer, then the hidden layer, then the output layer sequentially. Okay. Model equal to tf dot again. So you would be wondering what is this sequential dense. So basically these are already defined functions, ready to use functions given by the class TensorFlow Keras, which we can use directly. So if it were not for these classes, you would have to write the code on your own for building a dense network. But since has already been done by this library, we are at liberty of directly using it, because we want our main focus should be to build a neural network, and not the redundant or not the predefined, like the hard work of making a dense layer, because this making a dense layer or making a sequential model is same for all the neural networks. So that's why it is given to us as a ready to use function. Okay. So did I run this? Yes, I did. Okay. So now, see, again, as I told you, we will use the loss as mean squared error. This mean squared error loss is nothing but what I explained, that we use. Oh, sorry, we use that we say that the actual loss is square root of the squares difference between the squares of the predicted values and actual values. Okay. So let me just compile this model. Like, if you have any queries, please write to me after the session or after the event, so that I can clarify them. Because yeah, I mean, because it might be completely new for some of you. For some of you it might not be that new, but yeah, if you have any queries, please feel free to ask. Okay. So this step, this was just like defining. Yeah. And what is an optimizer? TF dot, again, there are different types of optimizers. So we are using Adams optimizer here, and this is also known as the learning rate. So what is the learning rate? Learning rate is basically the rate at which you wish your model to learn. For example, and it is a value between 0 to 1. So so I mean, I can explain it to you in depth, but I think I'll run out of time. So yeah, if you know what a learning rate is, great. If you don't know, just shoot me a question. I'll explain it to you. So so then I have compiled this model. Okay. So I'll also share this notebook with you, so that you can explore it at your wish, at your whatever pace you are comfortable with. You can share, you can have a look at the notebook. I have this hyperlinks marked here, which would explain it to you in detail, what this learning rate is, what this Adams optimizer is, and you can like research it on your own. Okay. So did I run this? Yes. So now the next part is training the model. Okay, so basically this is again a fit function which is given to us by the Keras library, wherein it requires 4 parameters as inputs. One is the input data, which is your Celsius parameter, Celsius values. The output data, epochs. Epochs is basically how many times you want your model to go over your training data. Like number of this 500 means your model will go over this data, Celsius Fahrenheit data, 500 times to get a better accuracy. Okay, so let's run this. So it says finish training the model. So now we can display the training statistics, like how did our model perform, and we can plot the error versus the number of epochs. Okay. So matplotlib is again a Python library which is used for displaying graphs. So here, as you can see, when we started, like when at the 0th epoch, the error was mean squared error was very high. As in, you can see it was like 1750, and as and when the number of epochs increase, the mean squared error goes down, and you can see like after 400 epochs, the error was stable. As in, the error didn't reduce much. So we could successfully claim that our model has converged, and after 400 epochs, and the loss is very less. You can see, right? It's almost zero, but maybe some in the order of 10 power of minus 2 or 10 power minus 1. So this is a good accuracy, because our loss has really converged a lot. So now the next part comes to predict the values. Like when you say model dot predict, so again predict is a function which we can use. What, and these functions are not that hard to write. What will a predict value function do? You can yourself write a predict code. You just have to say def predict, and you have to take a value as your input. You can say input data, and then you say okay, and you all need also your model. Okay, and then sorry, and then you say so now predict means what? You have your model. Basically you have your model, which might be, you just have to apply that model to the input value. Okay, so whatever your model is, you can say, suppose, for I'll just give you an example. This I'm not sure if this is the model or not, but I'm just saying. So for example, if your model is a sorry model is 100, or let me say 111.8 into your input data square plus uh, 20. Suppose this is your model, then it's just a simple substitution, and you say model and then you, sorry, not model, your answer, your output value, output output is equal to 11.8 into input data square plus 20, and then you say return output. That's it. So this is your predict function. You just have to substitute the values. Okay, but all of these functions are given to us in as a ready to use by TF Keras, so we will just use it directly. But again, it's not that tough to write these functions also, but it's just that it saves time and some unnecessary effort. So yes, when we say 100, the model predicts the value of 211.3338, and let's see what is the actual value. So 100, if 100 is your Celsius, 100 into 1.8 plus 32. Okay, so you say it gives us 212, and what our model gives is 211.338. So pretty close. Oh, sorry, it's already done here. Yeah, so 100 into 1 point plus 32 is 212. So our model is like we're doing very well, because 211.3338 is good as 212. If we say like for example, if we say 200, let's see what happens. 393. And what will be the value if we say 200 into 1.8? It will be 36. Sorry, 360, and plus 32 will be 392. So the actual value will be 392, and our model gives 393.42. Okay, not that bad. Now let us visualize what is this model. So here, when I was explaining it to you, the predict function, I said that I don't know, like if I do control Z, yeah, so I assume this is the model. But let's now visualize what is the relationship that our algorithm has come up with. Okay, so yes, so now we'll look at the layer weights. So we call the, in machine learning term, we call it the call as weights and biases. So now let's look at this. Okay. Okay, so you can see the weights are 1.8, which is your input data, a parameter multiplied by input data, and a constant, which is 29.21. So do you see the difference here? Actual formula is 1.8 times Celsius plus 32, and our model comes up with 1.8218 and 29.21. So this is actually very close to the ideal formula, to the original formula. So then that means our model has done a pretty good job. Okay, so yeah, that's what it's written here. And now this we did with just one input layer and directly the output layer, with in between no hidden layers. Okay, so now you can, this is an example, or this is a snippet wherein I have taken multiple layers. I say L0 is your input layer. Okay, and I say four neurons. So I decide to take 4 neurons in the input layer, not just one. Initially I took just 1 neuron, and then I define a hidden layer with again 4 neurons, and the output layer with a single neuron. So do you notice the difference here? Here we have 3 layers. Earlier we just had a single layer. We just had a single layer with 1 neuron, and here we have 3 layers with input layer having 4 neurons, a hidden layer having 4 neurons, and an output layer. So again we can say that, okay, model equal to tf dot keras dot sequential L0 L1 L2, meaning L0 should come before L1, L1 should come before L2, as simple as that. And again, model dot compile, same steps which we did earlier. Model dot compile, loss, optimizer Adam, model.fit, and finish training the model and predict. So let's see now what this model predicts for 100. Okay, so this model predicts 211.74745. And what did this predict? Let's see. 211 point. Okay, so I think it's same. Yeah, it's same. But when we visualize the weights are not same, because here there would be, as I said, as I told you, you remember, there would be one function which would take this input neurons to this hidden layer, then some another function which maps this hidden layer to this hidden layer, and a final function which maps this hidden layer to the output layer. So similarly, there are three weights. Oh, sorry, three weights. Yes, the one which takes us from L0 to L1, and the other which takes us from L1 to L2. So these are those. So these are the L0 variables. So I mean, these are some parameters, like internally they would have come up. This might be like this into x square, this might be into x cube, or whatever. And then these are constants. And so basically by applying these transformation, we get the layer L1. When we apply these transformations to L1, we get the final as L2. Okay, so basically this is the same problem solved using a different approach with more than one layer of neural networks. Okay, so this is how we like this is a simple demonstration of how we can use a neural network to solve a simple problem. But the actual scenario would be this one. I would just quickly explain you the problem, and then you can have a look. So we have a fashion MNIST data set wherein we have 60,000 to 1 lakh images. This is an open source data set. You can download it from Kaggle. So we have 60,000 images. Each images are classified into 10 classes. Like if it's 0, it means it's a t-shirt. If it's 1, it means it's a trouser. 2 is a pullover, and so on. And our aim is to build a model that, given a new image, not one of those 60,000, given a new image, our model should say, is it a t-shirt, is it a trouser, is it a pullover, is it a dress, or what is it? So this is our model, and this is where neural networks are actually used. So here you can see the input parameters are how many? 10, because every label corresponds to a different apparel. And output neuron will also be, output classes parameters would also be 10. In case of Celsius Fahrenheit, it was just one Celsius value, one Fahrenheit value. Here we have 10 values and correspondingly 10 output values. Okay, so this is a more complex problem. The actual power of neural networks lies, wherein neural networks would very easily and very in a computationally good manner solve this problem. And I also have the code to this. So but I guess I'm out of time, so I would stop here. But if you, I will share the code, or I'll share the code to of a code of this fashion MNIST with you, uh, and you can have a look. I'll explain it to you in briefly. Okay, so the steps are exactly same. I mean, there is no difference in implementing. We first, so what we did first, we just initialized the classes, we initialized our input data, then we created the model, we created some sequential layers, and then we compiled it, and then we trained it. So the same steps. Okay, exactly same steps. So we again import libraries, import here we import dataset also, because we are downloading it as an open source dataset. Earlier this dataset was very small, so we manually wrote it. We manually like initialized arrays. We manually initialized arrays, but here there would be 60,000 images, so it would be complex. So we are just importing the dataset from Kaggle. Okay. So okay, this will take time. Okay, meanwhile it runs, I'll explain to you later. So this is again like import numpy, as I said, matplotlib, again logging, so on. So yeah, so here we say dataset is tfds, like TensorFlow dataset dot load fashion MNIST. So when you load this dataset, you will have 60,000 images in your dataset and corresponding labels. Okay, wait, let me check if it's done. Yes, it's done. So if I say import TensorFlow, if I do this, yes. So it's downloading this data set. It will take some time because it's a huge data set. And basically so your data set would contain just labels, labels as output, and then you have to map those labels to t-shirt, trouser. So we have to do that. So we have to make a class names list wherein we say t-shirt, trouser, like in the same order, because zero is a reference to t-shirt, and sorry, and one is to trouser, and so on. Okay. One second, this is done.
Hi, Akhil. Just a time check. We have 2 more minutes to end up this, and then we'll move on to question and answer.
Okay, yes. So then maybe I'll stop here, because I'll be anyway sharing this notebook. So I
Absolutely.
have also included the code snippets, and I have tried to make it self-explanatory. So you can have a look. It will be self-explanatory, and if you still have any queries, you can come back to me. You can have my Twitter handle or whatever, and you can reach out to me. I'll be happy to help. So thank you, everyone. Thank you. I'll stop sharing.
Thank you so much, Akhil. What an enlightening talk. I'm sure this session will definitely help our community members to jumpstart on the most exciting or most sought after technology today, which is machine learning. There are a few queries raised by audience, Akhil. So we would like to go over those queries now.
Sure.
Just 1 second. So there's one question by Ismail Paris. Is like, what is the difference between TensorFlow and PyTorch?
Okay, so TensorFlow and PyTorch are basically machine learning libraries, and when I say machine learning libraries, they provide us with a tons of capabilities. Like in the code I mentioned, I use TensorFlow. So TensorFlow gives support for making a neural network, for making a dense layer, and similarly PyTorch. So there is not as such a difference between TensorFlow and PyTorch. It is just they are just two different libraries having own set of compatibilities, own set of approaches. uh, so there are some features which are there in TensorFlow and which are not there in PyTorch. So, for example, TensorFlow has an object detection API enabled in it. PyTorch, it's not that good in PyTorch. So basically, they are just two different libraries to achieve the same thing. Some people are comfortable in coding in TensorFlow. Some people are comfortable in coding in PyTorch. It's up to the user to use whichever library he feels is better suited for him. So if you want, you can explore both and you can choose one. I mean, there is as such no difference between TensorFlow and PyTorch, just two different machine learning libraries having their own capabilities and having their own functions and having their own unique capacities and also limitations. Like both of them have their own limitations.
Okay. Okay. Another question is from Mohan. Uh, and this question has come from multiple people. Which course or getting started material you would suggest?
So yes, I always suggest a single course as a starting point to people who are new to machine learning, and that is the course by Andrew Ng, which is freely available on Coursera of Stanford University. That course is of 2005, but it is still so relevant and so. I mean, that is like the beginning course. I mean, no course is better than the Andrew Ng machine learning course from Stanford of 2005. I mean, course was recorded and was played 10-15 years ago, but it's still so relevant, and nothing beats that. Like, that is the intro. If you want to kickstart your journey, then that is the go-to thing. Like, it's the best. It will give you a grasp of the mathematics as well as the machine learning technologies, all the algorithms. It's very good. I mean, it's the best according to me.
Okay, fine. The next question is from Pratham. Uh, his question is, has machine learning its own causes, like less manpower and leading to more unemployment? What is your take on that?
Okay, so no, so yes, one of the aspects is correct, that it automates some processes, but those processes need to be automated, because for example, if you are just doing a menial job of, like, maybe switching off the VM, or maybe I mean it, there are people who are doing it. I mean, it's not an hypothetical situation. There are people who are just for powering of the VMs. So it can be easily automated, and And those people can be utilized in a better way. I mean, their skill set can be developed in a more better way, and they can be deployed somewhere else. So it is not that it is leading to unemployment. And this is one aspect, but there are some other aspects wherein people are actually not capable of doing it. So for example, in one of the projects I made, there were 800 emails coming on a daily basis, and a band 20 people were just involved to take care of those 800 emails. So this is like a waste of time, because and this job can be done within 2 hours by a program, by a code. So those 20 people can be better utilized in some other domain. So it actually doesn't lead to unemployment. It basically it makes better use of the manpower, because we humans are way more capable than a machine. So in terms of intellect, so our efforts should be better utilized in doing intellectual tasks rather than doing mundane repetitive tasks which can be easily done by a machine. So that's the beauty of machine learning, that we it involves us to it motivates us to do better things in life, that which machines can't do. I mean, machines can't write code to deploy a machine learning bot, right? So that is something which we have to do, or we do. So yeah.
Absolutely. I agree with you. Okay. The next question is from Mohan. He says, how can we use loss function and optimizer function to get better accuracy? Can you please elaborate on this?
Yes, sure. So this depends on the problem which you are dealing with, and also the algorithm which you are choosing to solve it. Okay, so for every problem you can use any algorithm. Like for this fashion MNS, you can use neural nets, SVMs, whatever. Okay, but if you ask how do we choose loss function and optimizer function, so basically that depends on what. So in neural networks also, if you're using the ReLU activation unit, and there are different types of sigmoid neurons. Okay, I didn't go in the maths in this session, but there are different types of optimizer functions. Like one is your sigmoid function, one is the ReLU. So each there are different loss functions suited for different types of functions. So for example, if you use sigmoid neuron, we use the sigmoid function for optimizing loss. Okay, and so yeah, it basically depends on your problem statement and also the algorithm which you choose. But for a generic idea, for a generic response, the most common loss function which is used is mean squared error, because 90% of the times we use mean squared error, because it works very good, and it gives us a good sense of the accuracy. And for optimizer function, there are tons of optimizer functions, and that actually depends on the problem which you are solving. So so yeah, I mean, optimizer function is something which is like problem specific and algorithm specific, but mean square error is the most generic. I mean, if you are a newbie and if you are not sure which loss function you should use, just go for mean square error. It will not give bad results, definitely.
Okay. So the next question is from Swapnil. Uh, he says, what are the basic topics of statistics one needs to get familiarized with before starting up with the machine learning?
So there are no such basic topics. I mean, basic as in very basic, which you would have already, like, which everyone would know, are like mean, median, mode. That's it. What is the mean? What is the standard deviation? Those topics. Like what are the definitions? What does a mean? What is meant by a mean, mode, standard deviation, and that's all. Because the course which I said, Andrew Ng, Stanford, Coursera, Introduction to Machine Learning, he explains everything in detail. So there is no prior knowledge assumed in that course. So at least, especially of statistics. So there is no such information. I mean, if you know what is a standard deviation, what is mean, what is median, what is mode, that's more than sufficient. There are no such prereqs.
Okay. The next question is from Wild Sheikh. He says, how do we decide how many layers we should use for a particular problem? Are there any pros or cons of using more or fewer layers?
Yes. So yes, there are pros and cons of using more or fewer layers. And how do we decide? So we decide. So okay, So this is something which is a trial and error based decision, which we come up with experience. As in, for example, if you are in the domain for say 1 year and you have solved deep learning problems, so you would know, okay, this problem would probably require 5 dense layers or 6 dense layers to solve. And how to decide is just you can just try with various layers, see what the accuracy your model is giving, and go on. I mean, suppose you can start with 1 layer, you see, okay, your accuracy is 90%, increase it to 2 layers, 3 layers. But the con is that as soon as you increase the layers, the your model becomes computationally intensive. So what that means is it will take more time to train, it will become heavier, it will take more time to predict. So all the problem which we solved was very very basic, but when we go to real life problems, the inference time matters. So your model must not be huge, like, so you can get 119, like very high accuracy, 99.9% accuracy, but then the latency would be very high. Like for predicting one value, it would take 10 seconds, and that's not feasible. So there is a trade off. So you have to decide on your own that do you want latency or do you want high accuracy, and what is the best number of layers that suits it. So in some cases, increasing the number of layers won't help. So that is your, like, that is the depends on the problem. So you just have to try. If increasing layers helps, okay, good, great. But there is a trade-off that model becomes more computationally intensive and heavy. So yeah, these are the pros and cons. Usually more number of layers would mean better accuracy, but not true. I mean, not true in all the cases. Usually that's the case. Yeah.
Okay, so that brings to an end of Q&A. I thank Akhil once again for helping our community members to get started with ML. The scope of today's talk was only to give a gist about what ML is and how can it be used to help real world for solving real world problems. If you liked our today's talk, please comment on YouTube video, and we can plan for more detailed trainings or even the hands-on training on machine learning. Uh, One announcement that we want to make from GDG Cloud Mumbai team is we have recently migrated from meetup.com to gdg.community.dev portal. With the start of 2021, we will have all our events announced only on this portal. So please get registered yourself on this portal and be connected. Thank you so much and wish you Merry Christmas and very Happy New Year. Thank you so much.